Hey, hello geometry students. Welcome to lesson 10.6. We are now getting into not surface area, but volume. So in three-dimensional shapes, we want to know how much two-dimensional surface is on these shapes. But then we also want to know how much space they take up, and that is volume. And so we've got a couple definitions and about 4 questions to go through. So let's jump right in. Volume of prisms and cylinders, because we can treat those pretty much the same. So first of all, definition, what is volume? Well, my definition I'm going to use is just volume is the amount of space, length, width, and height that an object occupies. So again, surface area is like the accumulation of all the two-dimensional surfaces, again, like wrapping paper or maybe the amount of paint it might take to cover something. That's surface area, but volume is now space. How big is something? And so the key thing here is our units now change. When we talk about volume, we're talking about not units squared, because you basically have linear distance. This is a quick set of examples. You have linear distance, and we would call that 1D. And then we have square distance, or square area, and that would be 2D. And now we're talking about taking that and putting it in 3 dimensions. So now the units are not centimeters or centimeters squared, but they're going to be units cubed. Okay, this would just be units, this would be units squared, and this would be units cubed. So my awesome little square that I've drawn over here, we can use it to see that its length is, let's see, 1, 2, 3, 4. Its depth is 1, 2, 3, and its height is 1, 2, 3, 4, 5. So 5 right here. Okay, so we want to know not how much surface it has, but how much space is it going to take up. And as we'll see in the next definition, we'll talk about how to solve that. Okay, so let's go ahead and look at what is the volume of a prism. Okay, and let me add to this, included in this prism or a cylinder. And you'll be pleasantly surprised, I think, of course, that volume is a little simpler than surface area. Where in surface area, you have to find first that lateral area, then you have to add on the 1 or the 2 bases, depending on the shape. Volume is a much quicker process. Volume is simply base times height. Because if we think about, go back to the little square up here, if we know how many, go to this color here, if we know how many blocks are here, and we could call this the base, then that's a certain amount of area. And then if I just multiply that by the height, how many times that area is stacked on top of itself, that tells me how much space something is going to take up. So in my example here, I can see that my base, if I say volume equals base times height, I could see that the base would be 3 times 4, which would give me 12, and then the height would be 5. So 12 times 5, we're going to get 60 units cubed. Okay, and if you counted up all the little blocks that I've drawn there, you would see there are actually 60 blocks in order to illustrate that that is, in fact, some number that makes sense. If we go to my second example here, this is a nice little rectangular prism, and we can see, okay, let's find the base. So the base is, again, volume equals the base times the height. Just the base would be 10 times 12. Rectangles are nice and easy. Okay, and then the height is 8. So in this case, we're just multiplying all 3 numbers together. And so we're getting 120 times 8. Let me crunch that. And so we get 960, in this case, centimeters cubed, because we're now talking about 3 dimensions. So the volume is 960 centimeters cubed. Okay, so whatever prism you have, find the base area, and then just how high is that stacked times the height. So much quicker, much simpler in most cases than surface area, I think you'll find. So that's volume of a prism. We'll get to other shapes in 10.7 and 8. But let's look at our questions. So question 1 is, how does the volume formula for a prism change depending on its base? So this is the point I was kind of trying to make, but something to consider. Your formula is very generic. It's simply volume equals capital base times height. But again, that base is always going to change depending on the base that you have. So in my first example here, let's just say, pretend this is a square. So this is going to be side squared. My base is found by doing side squared. Whereas if my base is a circle, then my base is going to be found by doing pi r squared, the area of a circle. In each case, once I find my base, then I'm going to multiply by h, the height. Okay, if I happen to get lucky and I get this wonderful 1, 2, 3, 4, 5 hexagon, so if my base is a hexagon right here, then when I calculate my base, I use all the formulas I've learned from the previous chapters, and that is 1/2 apothem times the perimeter. Okay, that's one's probably the most work and the one you might end up dreading the most. So 1/2, let's clean that up a little bit. Okay, but again, find the base. And then finally, lastly, you could have something like a triangle, in which case you're going to find capital B by doing the triangle formula, which is 1/2 base times height. Notice that little b base is not the same as capital base. Capital B base is always, this is always base area. Okay, so B is always going to be different depending on the type of prism that you have. Okay, find that area and then just multiply by the height. Okay, question number 2 asked, how does volume change according to changes in the dimensions of a prism? So we had this with area and perimeter. So what happens when you get into the third dimension, when you get into cubed? Well, therein lies the clue, but let's just go ahead and take a look. I got a nice little square here. Okay, and we'll just call it 1 square unit. It's 1 by 1 by 1. So we'll say its volume is 1 unit cubed. Okay, and now we've got this guy over here, and it's been tripled. Okay, so now we've got 1, 2, 3. And it's also now 3 high. And it's also now 3 deep. So every dimension has been tripled. Well, what's the volume of this? Well, let's calculate it. It would be base 3 times the other base, 3 times the height, 3. So 3 cubed, that's 27 units cubed. So what happened? When I tripled, in this case, I tripled the dimensions, how much bigger did the entire volume get? Not 3 times bigger, not 9 times bigger, but 27 times bigger, or 3 cubed. Okay, and so that's kind of the key here, because now we're in 3 dimensions. Whenever you have a scale factor of x, the change is always going to be that change cubed. So for example, if I double the size, then I'm going to get, it's going to create a change of 2 cubed, or 8 times, it's going to be 8 times bigger. Okay, or say something's 4 times bigger. Well, then that's going to be 4 cubed, which is 4 times 4 times 4, that means it's going to be 64 times bigger. And you can see visually with the cubes here on the left how just changing all 3 dimensions doesn't just triple it or 6 times bigger, but it's going to be 27 times bigger. It makes a big difference to add on or to multiply all 3 dimensions. So again, whatever the change is, just cube it, and you'll know what change took place in terms of the volume. We could also say, like, say a small difference. Say it was changed by a third. It was reduced by a third. Well, then the overall change will just be 1/3 cubed, which will be 1/27th. Be much, sorry, you can't see that. It'll be much smaller. Okay, so linear distance change is just x. In terms of it changes to area, it's x squared, and in changes to volume, it's x cubed. Okay, number 3, just talking about units. How do the units of volume compare to the units of surface area? This is just a minor detail, but always to remind you that surface area, this is a net of actually it's not an accurate net, it needs a top, but a net of a rectangular prism, but that it's 2D. This is 2-dimensional. Okay, and so surface area, I'll put it right here, surface area is always units squared, because all you're really dealing with is length and width. Okay, you've just got 2 dimensions, length and width. And so that's again, that's a flat surface. Whereas now that we're into volume, now you have length, width, and also height. Okay, so volume therefore is units cubed. So obviously you want to be accurate with your units, but there's also a big clue in terms of various difficult questions. If we're talking about volume versus surface area, you're going to see the difference in the units. Surface area is going to be 2-dimensional, units squared. Volume is going to be 3-dimensional, units cubed. And lastly, just a sample problem with a cylinder. Number 4, what would be the volume of a cylinder with a height of 12 meters and a radius of 6 meters? What would the volume be? And then we'll talk about the changing of the dimensions. But first, let's deal with this one. Well, what's our formula for volume? V equals the base times the height. What kind of shape are we dealing with? We're dealing with a circle. So that means the base is actually going to be the area of a circle, pi r squared times the height. Okay, and now we can go ahead and plug in our radius. They give it to us straight away. Pi times 6 squared. And what's our height? Our height is 12. So now we can crunch that. That is volume equals 6 times 6 is 36. 36 times 12 is 432. We're going to get some big numbers when calculating volume. So 432 pi meters cubed. Okay, because we're in 3 dimensions of volume, talking about space. If you want to leave it in terms of pi, there you go, you have it. Or you could crunch that number. It gets even bigger. Don't be scared by the big numbers. 1356.5 meters cubed, approximately. Okay, so either of those are an acceptable answer. Some questions will actually want you to have both in terms of pi and it's rounded to the nearest tenth. Okay, so base times height. It's pretty simple. You just got to know how to find the base areas of the various shapes, whether it's a circle, triangle, rectangle, square, or regular polygon. Alrighty, now the second part of this question, just to see it in action, is what would happen if the dimensions were reduced by a third? So what would happen if instead of 12, this was actually just 4? And what would happen to this if the radius instead of 6 was actually just 2? So they were each a third smaller. Now, I could recalculate all that, but we want to learn the shortcut. If I'm being reduced by a third, then we're talking about volume, then I know the overall volume is going to change by 1/3 cubed, which is 1/3 times 1/3 times 1/3, or 3 times 3 times 3, 1 times 1 times 1. And so that's going to be 1/27. Okay, so that means the volume of a cylinder reduced would be 1/27 of what I got here. And if I actually wanted to find that, I could go ahead and take my 1356.5 and I can divide this number. I mean, I won't do it right there, but I can take my 1356.5 and I can just divide by 27. Okay, multiplying it by 1/27. And so if I divide it through that, I get 50.2 meters cubed. Okay, so short answer would be it's reduced by a 27th, or 1/27 the original size. Or if it actually had me to find the new volume, I can then just multiply that 1/27 by my volume. Or you could see if I went ahead and resolved the problem with 2 and 4 instead of 6 and 12, I would get this exact same answer. But I won't make this video any longer than it needs to be. Just come to class with any questions, and we'll have a good time talking about volume. Next lesson, I only have one more lesson. It's a combined lesson, and it's going to be just a few more other shapes and how to find their volumes. All right, see you in class.